Hello, class. So on this video, we'll continue on section 2.7. In the previous video, we actually went and worked by hand a little bit of how this algorithm that we have is going to work, right? Remember, this algorithm was to find or approximate values of a solution to a first order nonlinear, so it doesn't have to be linear, initial value problem. So this is a summary. Again, the first thing we did is we actually verified that a solution exists, right? We used theorem 2 of section 2.4 for that, right? There's no point in trying to approximate values of a solution if that solution doesn't even exist. Then the method, which I'm just going to explain with this picture here, was very straightforward. So what did we do? So we had this function y, right, in red. We wanted to approximate the value of y of 2.1. So what did we do? Well, what we do in Calc 1, right? We know what, and this is 2, I think this is the 0.24 actually. Yeah, it should be the 0.24 here. Okay. So what is it that we did? Okay. So we knew that the 0.24 lied on the graph of y. We also know what the derivative is because we're given that dy dx is some expression of f of xy. Right? So what did we did? We found the equation for the tangent line to the graph of y going through the point 2, 4. Right? And that's what we called L sub 1 in green. Right? That's the linear approximation, which which is the same thing as the equation of the tangent line. Okay? Now we use that as you do in Calc 1 to approximate y of 2.1. Why? Because for x value is really close to 2, L1 is a good approximation. Right? So that's what we wrote here. Now, let's say we also wanted to approximate y of 2.2. Well, instead of just using the same L1, since as I mentioned, the further away you move from 2, the worse the approximation is going to be, right? Using this linear approximation. So instead, what did we do? Well, we, instead of approximating, or I guess what we did first is approximate the value of y of 2.1, right? So instead of using this first linearization that we did, we move to this point that it's approximating what 2.1 y of 2.1 is. Okay, so this is approximating 2.1 y of 2.1. And instead of just plugging in 2.2 into the first linearization, we create a second linearization based on this point. And you see, this is not a point that lies on y. It's a point that lies on the first linear approximation that we did. But then the process is the same, right? We do the second linearization and we use that to approximate y of 2.2. And again, the hope is that the approximation we do in this y coordinate takes care is more accurate in the end of the algorithm or of the process that we're doing than actually just evaluating the first linearization. Okay? If we want to do it again, say we want to approximate y of 2.3, well, we do a linear approximation about this approximate point, right? 2.2, 4.38. And we keep doing this, right? This process. And it's an iterative process, meaning that if we want to approximate now y of 2.3, 2.4, etc., we just use the previous point and use a new linear approximation. Okay. So let's write a general method for this. So we can actually have a general formula that we can easily put into a computing software. Okay. So given a first order initial value problem, not necessarily linear, dy dx equals phi of xy with the initial condition y of x naught equals y naught. Right? What we're going to do is we're going to fix a positive number h. Okay? So h in our previous example was 0.1, right? Because we started at x naught equals 2, we moved to 2.1, we moved to 2.2. So each time we're just adding 0.1 to the initial x coordinate 2, right? So 2.1 is 2 plus 0.1. 2.2 is 2 plus 0.1 plus 0.1. Okay? So we fix a number, positive number h. which is going to tell us how we move from the first x naught, so the first input, to the next input, to the next input, simply by adding h. Okay. So suppose we want to approximate y of x naught plus h, right? So we want to approximate a y value that is not given to us. Okay? Let's call this x naught plus h, let's just call it x1. Now we're going to call this approximation y naught, y sub 1. Okay. And again, we only can do an approximation for this because we don't exactly know what y of x1 is unless we actually find the solution y, which we're trying not to do. And again, in a lot of times, you won't even be able to do that. So we have to do this a sort of approximation process like this one. Okay? So what do? We do a linearization, right, about the first point, x naught, y naught, which we know lies on y. Right? And using the point slope formula, that has this form. Y naught plus the slope, which is just the derivative evaluated at x naught, y naught, right, times x minus x naught, right? That's just the point slope formula. Okay, so how do we find y sub 1 from this? Well, you just plug in x1 into this linearization, right? x1 is x naught plus h, right? So I simplify this, I get y naught plus phi of x naught y naught times x1, we're replacing x with x1, right? So x1 is x naught plus h. The x naught here and the x naught here cancel, and this simplifies to y naught plus phi of x naught y naught times h. Right? So we have this new point x1 and this approximation of y1, right? Of what? So this is approximating what y of x1 should be. Okay? So that's just the first part, the first iteration of our algorithm. So I'm only gonna do this by hand twice, but you're gonna see that there's a pattern that follows. Okay. So now, suppose we want to approximate x naught plus 2h, right? So we move from x naught to x naught plus h. That was the first approximation. Now we move from x naught to x naught plus 2h, right? Which is x naught plus h. Okay? We call that new value x naught, x sub 2, right? And the approximation that we're going to get is going to be y sub 2. Okay? So what do? We find a linear approximation about this approximate point, right? We're using x1, which is just x1, but y1 is an approximation for y of x1, right? So this is where we're in the picture about before. What are we doing? We're finding a linear approximation that goes through this approximate point and not the actual point that would be here, okay? Because we don't know what that point is. So we just plug everything in, right? By the point slope formula, what is this linear approximation going to be? Well, it's going to be the y value plus the slope at this point, right? So phi of x1, y1 times x minus x1. Now x1 is just x naught plus h. So I'm just going to replace x1 here with x naught plus h. Okay? So that's the second linearization. Right? That would be this line in orange here. Now we want to use that to approximate y of x2, right? So what do? Well, we plug in x2 to this approximation. Okay, so we have y naught plus phi of x1, y1. We replace x with x2, which is x naught plus 2 times h. After you simplify that, you're left with this expression, right? So y2 is equal to y1 plus phi of x1, comma y1 times h. Right, so we get this new point, x2, y2, where again, y2 is an approximation for the actual value, y of x2. And we keep doing this process again and again and again to approximate each new y value, right? Now, the pattern I want you to see is that y1 is given by y naught times phi of x naught, y naught times h. y2 is given by y1 times phi of x1, y1 times h. So what is this telling us? Each new function value we're trying to approximate is dependent exactly on the previous y value and the previous x value. We just plug them in into this formula. Right? So what is this formula in general? In general, the nth approximation that we're doing is just dependent on the previous one, right? So y of n minus 1 times h times phi of x n minus 1, y of n minus 1, right? And this is something that you can easily plug in your computer. Why? Because using this formula and using the fact that x naught equals, well, whatever your initial condition is, right? So we have the point x naught, y naught, which comes from the initial condition, right? So this comes from this. Well, as long as you have this first point, you can just compute or plug in this formula into your software, and it will compute each successive. Oh, and this looks like a y1, sorry. As long as you have this initial point, and you know that this formula is what's following, right? So each y sub n is given by this formula. Well, you can just plug that into a computer, and it'll do all the computation for you. Okay? So it's as simple as that, right? This is all the information you need, and this first point, you plug this into a computer, and it's going to spit out y1, it's going to spit out y2, it's going to spit out y3, and in computing each of these, it's using the work from the previous one. Right? It's using y1 from the previous one, it's using y2 from the previous one, etc. Okay? This is what we call an iterative process with initial condition or a starting value given by x naught, y naught, which of course comes from this initial condition that you're given to begin with. Now, you'll see a lot of iterative processes in classes that you see in the future, especially in classes like numerical methods, more advanced ODE classes, more advanced PDE classes. You're going to see a bunch of these. But this is the first one we're going to see, and this has a name. It's called Euler's method. So it's a simple process. As you see, there's not anything deep going on in it. We're just using linear approximations centered at new points each time, right? So there's nothing crazy. Like there's nothing here that we didn't learn in Calc 1. The only thing that's new is how do you go from a general method and write it in a way that you can fit it into a computer, right? And that's what we did in this slide here. Right? We're trying to find a pattern, right? Or what you could also call a recurrence relation. Right? So it's something when you have an input or an output that depends on previous outputs, that's what you call a recurrence relation, okay? Or an iterative process, right? Either way. In some classes, you're going to see it as a recurrence relation. In some classes, you're going to see it as an iterative process, okay? So this is the only thing that's new. Trying to find a pattern for this iterative process so that we have a way to feed this into a computer so we don't have to do it by hand, right? Because a lot of times, let's say we wanted to approximate y of 3. Well, starting from what we knew, that y of 2 equals 4. Well, we would have to run this process, let's see, 0.1, so 10 times to get to this. We don't want to do all this work 10 times that we did here, right? So instead, we just have a general formula and we give it to a computer. Okay? So this is what Euler's method is. So this is going to be the end of this video. In the next video, I'm going to show you how we can do this in Mathematica. And again, all we need is the initial condition, the derivative, of course, and that's it. With that, we can just evaluate this. Now, of course, there are some things to think about. You know, anytime you're doing a iterative process to approximate something, there's the question of what is my error? How far away is my approximation from the actual solution? Right? Now, error analysis is a big thing about iterative methods. In fact, there are PhDs and there are papers just written about error analysis for a given algorithm. Now, of course, we're not in a level where we can study that error analysis. Right? It's obvious in the picture that there is some error, right? As I drew in these vertical lines, right? The value for the function that we're approximating is not the same as the actual function value. Right? Now, that's all we can do as of now with the level of knowledge that we have. Right? When you get to more advanced classes, you're also going to be able to do some error analysis. Like, can you bound the error? For example, even though you know there's an error, can you say that the error is less than something? That would be nice, right? Especially if that something is small. Okay. You'll be able to do that in further classes. For now, all I want you to see is that just using common things that we learned in Calc 1, we can use or derive this method that can allow us to calculate values of a function which we don't know. Again, just as approximations, but still. Okay? Whether those approximations are good or bad, so what is the error? Well, we can't do that yet. But hopefully, as long as our direction field, so the derivatives at each point, as long as they're not too crazy or too big, this should be a relatively good enough approximation.